Okay, so we have learned that if you take nonmetals and nonmetals and put them together, we end up with these things called covalent bonds, or sharing of electrons. We even built some simple molecules like H2, Cl2, N2. But what we're going to do is we're going to try to make some bigger molecules today. So first things first, we scroll back up, because I don't know why it decided to scroll down. And we're going to predict some molecules. So we can kind of do this. We did it with CH4. We said, hey, if there was a carbon and 4 hydrogens, then we'd end up with those hydrogens sharing the electrons with the carbon, something like that. And of course, we now have our simpler way of drawing things using the lines. And so we can draw CH4 looking like that. What if we had other things? Well, if we had a sulfur and 2 hydrogen atoms, okay, what would that look like? Well, sulfur, he's got how many valence electrons? 6. 1, 2, 3, 4, 5, 6. Hydrogen has 1. And so we might guess that those hydrogens are going to share one of their electrons with sulfur. And now sulfur, if he looks around him, sees 8 electrons. And we're pretty happy. So it's not too difficult to try to put together some simple molecules. Where some things get a little more complex is if, like, say, we wanted to do boron. Boron has 3 valence electrons. And if we wanted to do some chlorine atoms with that, what would that look like? Chlorine might go here. I'm doing the dots for now, but I'll do the lines in just a moment. And if you look around boron, you only see 6 electrons. So what's going on there? Because it turns out this is actually what you get. And if we draw it with the lines, it looks more like this. One of the things I like to do when doing chlorine is do my electrons in a different color, because that L in chlorine looks like a pair of electrons. So there we go, boron trichloride and some other things. But what we really want to do, since we're scientists and we really want to be good about this, is we want to have a set of rules. How do we make molecules? How do we put them together in a way that's systematic, that we always get the same answer every time, and we get the right answer every time? So what we need is a few rules. And you're going to use these rules anytime you want to build small molecules of covalent compounds, so nonmetals to nonmetals. And the first thing we're going to do is we're going to count all of our valence electrons. What we're going to do is we're going to do each one of these steps one at a time, and we're going to do it for 2 different examples. We're going to do it for CO2, and we're going to do it for NH3. Now for CO2, we're counting valence electrons, and what I mean by that is we're going to look at each of the atoms in there, figure out how many valence electrons they have. Carbon has 4, oxygen has 6, but there's 2 of them, so 12 plus 4 is 16 VE for valence electrons. Nitrogen has 5, hydrogen has 1, but there's 3 of them, and you add that up to get 8 valence electrons. So we know how many valence electrons are in each one of those. In our next step, we are going to pick a central atom. If we're going to have a molecule, there has to be one atom that's in the middle that everybody else connects to. And for small molecules, there's one atom in the middle. When we get to bigger, larger molecules, especially towards the organic chapter at the end, there's going to be a bunch of ones that are acting as central atoms, and it's because they're going to have several things connected to them. But for now, just one central atom. How do we pick the central atom? The official rule is the least electronegative atom is our central atom. However, we don't know what electronegativity is yet, so I'm going to give you a slightly different rule. Gets you pretty much the same result. Okay? Let's look over here. We've got carbon and oxygen to choose from in our CO2. Carbon has 4 valence electrons, oxygen has 6. Right? How many more electrons does carbon need to be happy? Right? He needs 4 to be happy to make 8. Oxygen needs 2 to make 8. Well, this 4 and this 2, that's how many bonds carbon is likely to make and how many bonds oxygen is likely to make. Because remember, each time they share with somebody else, they make one covalent bond, they see one extra electron from that thing they're sharing with. So carbon's going to make 4 bonds. Remember, we had CH4 when we were talking about it. So carbon makes 4 bonds, oxygen makes 2. And how we pick the central atom is you pick the one who makes the most bonds. Why? How I think about it is this. If you're going to have someone who's going to act as the busybody in the middle connecting everyone, don't you want the person who's best at connecting? The person who can make the most different bonds. I think that makes sense. But like I said, that's also going to get you the least electronegative atom. The only challenge there is, let's say you have 2 atoms that you're deciding between, say, sulfur and oxygen. They're both in the same group on the periodic table. They're both 6 valence electrons. There, you're going to use the one further down the periodic table. So you'd have sulfur as the central atom versus oxygen as the central atom. How about nitrogen and hydrogen? Nitrogen has 5 valence electrons. He needs 3 to be happy. Hydrogen has 1 valence electron. He needs 1 to be happy, because remember, he's looking to look like helium. So who's going to be the central atom? Somebody who makes 3 bonds or somebody who makes 1 bond? Well, if you make 1 bond and you make a bond to somebody else, the molecule is over. And so that's not a very good central atom. So we're going to put nitrogen as the central atom here, carbon as the central atom here. Okay, once we pick the central atom, what we're going to do is we're going to draw a single bond from the central atom to each of our, what we call, outer atoms. Okay, so what do we have? We have carbon in the middle. We have nitrogen in the middle here. What are our outer atoms? Our outer atoms are our other atoms. So we've got an O here, an O here. And we've got 3 hydrogens here. Doesn't matter exactly where you put them. You could put that second hydrogen on the bottom, on the top. Doesn't really matter, as long as most people generally write them at 90-degree angles to start with. More complex ones, you can't do that anymore, but for the most part, 90-degree angles and you're all good. So I drew single bonds from the central atom to each of my outer atoms. If I didn't have those bonds, I wouldn't have a molecule. Step 4 is to count the electrons that I used and subtract from the total. And we're going to place remaining electrons in pairs. Always work with electrons in pairs when you can, which is 99.9% of the time, and in this class, 100% of the time. Place the remaining electrons in pairs around the outer atoms. That's very important, until you're full, or you run out of electrons. What does that look like in this case? So I've got my CO2 here, and I've got my NH3 here. And in step 1, I figured out that here I had 16 valence electrons. Here I had 8 valence electrons. But what did I do? When I drew this bond here and this bond here, what did those bonds represent? They represented a pair of electrons, 2 electrons. So for each one of those bonds, I used 2 electrons, which means I used 4 in total. Here, I used 2, 4, 6. Right? And so I have 2 electrons left over here, and I've got 12 electrons left over here. And then what I'm going to do is I'm going to put those electrons around my outer atoms until those outer atoms are full. So I've got 12 electrons. I'm going to start over here by putting a pair. And again, we always count by 2s, just because it's easier when we're doing these kind of things, because it almost always comes in pairs. We're going to say 2, 4, 6. And I'm going to stop on that oxygen. I could have picked the other oxygen, but I'm going to stop on that oxygen. Why? Because now that oxygen sees 8 electrons around it, so it's full. So I've only used 6, so I've got 6 more. 2, 4, 6, 8, 10, 12. And now I've used all my electrons. This other oxygen is full. Let's go over to the NH3 example. I've got 2 electrons left. I'm going to start with my outer atoms. What about that atom there? Well, hydrogen is already full, right? He is happy looking like helium, so he's already full. Well, and the other hydrogen's already full, and the other hydrogen's already full. So there's nothing I can do in this step. It's important to do this step first. Put your electrons on the outer atoms first. People get tempted to skip this step and start putting electrons on inside atoms. They put electrons on double bonds. Don't do that, especially when you're just starting out. You'll make some major mistakes. All right, so that was step 4. Now step 5 is to place any remaining electrons in pairs on the central atom. Well, okay, so what did we use? Well, on this left one, on the CO2, if I start counting, I used 2, 4, 6, 8, 10, 12, 14, 16. That's all of my electrons. I got nothing left. So there's nothing to do in this step other than to just redraw what we had. Oops, redraw what we had in the last step. Okay. So I'm going to put my carbon back here, and we've got like that. So I just draw my CO2 looking like that. On the right-hand side, my ammonia, NH3, what did I do? I didn't use any. I still have 2 electrons left, so I draw this from my last step. And now I can put an electron in pairs on my central atom by drawing that on my nitrogen right there. Okay, now we're going to do next what I call a happiness check. And what is a happiness check? We want to see if everybody's happy. And there's 2 things to a happiness check. One is all atoms full, right, which is an octet, or in the case of hydrogen, a duet is what they called it. And 2, we have the correct number of valence electrons. Now, you might think to yourself, why do we need to do that second step? Didn't we have the correct number to begin with? And the answer is yes. But it turns out when you start drawing lines and moving lines and erasing lines, it's really easy to lose track or to add an extra line here and there. So it's always good to double check that you did exactly what you wanted to. So our happiness check on our CO2 looks like this. We've got 2, 4, 6, 8, 10, 12, 14, 16. So we've got the right number of valence electrons. And then what we want to do is we want to look and see, do we have everybody happy? Okay, so we're going to look first at this oxygen over here. Is he happy? Well, yes, we see 2, 4, 6, 8 electrons that oxygen sees. And so he is happy. How about the middle carbon? Is he happy? We see 2, 4 electrons on him. That's it. That is not a happy carbon. And so we are not done. We did not pass our happiness check in this step, which means we're going to need to move on. On the right-hand side, let's look at this hydrogen. He's happy. He's got 2 electrons. Happy, happy. So we've got 3 happy hydrogens with 2 electrons apiece. What about this nitrogen? If we look, he's got 2, 4, 6, 8. He's happy. So everybody's happy. We passed the first half of our happiness check, but now we just need to count electrons, which is 2, 4, 6, 8. We had 8 valence electrons. We've now passed our happiness check, which means that for the ammonia, we are done. And this is actually the structure of NH3, a central nitrogen atom, 3 hydrogens single bonded to it, and then 1 extra pair of electrons on that nitrogen. This pair of electrons is not a bonding pair. It's not attached to anything, and we call it a lone pair. That's the name of an electron, a pair of electrons that's not participating in bonding. Now, CO2, unfortunately, we were not done, so we have to go on to step 7 for CO2. And step 7 is we're going to move pairs of electrons from our outer atoms to make double or triple bonds. Okay, so what do we have? We have CO2 on the left. And we're going to move pairs of electrons from our outer atoms to make double or triple bonds. So what does that look like? Well, we decided that carbon wasn't happy. And so carbon needs more electrons in order to be happy. But we can't just take one of these pairs of electrons right here on oxygen and move it over to carbon. Because let me show you what happens if we do that. If we take and move one of those pairs of electrons over to carbon, what do we have? We now have an oxygen over here who's not happy. He had 8 electrons, now he has only 6. So that's not a good result. So let's put that one back over here. So what we do instead is we take one of those pairs of electrons, and instead of moving it to the central atom, we move it to make a double bond in the middle right there. So I'm going to draw that right below, and it looks something like this. We now have a carbon double bonded to that left-hand oxygen. And if we look at this oxygen, he still sees 8 electrons around him. And if we look at our carbon, he's a little happier now, because instead of seeing 4 electrons, he sees 6 electrons, each line being a pair. But he's still not happy yet. So we're going to keep doing this, and we're going to keep moving these. Move one pair at a time. Don't try to move a bunch at a time. You might overdo it. So we're going to move another pair. Now, do we move another pair from the left to make a triple bond? Or do we move a pair from the right to make another double bond? The answer is nature always appreciates but doesn't require symmetry. Triple bonds are harder to make than double bonds. So when you have a chance to make a second double bond versus a triple bond, go ahead and do it. So I'm going to take one of these electrons, move it over here, and I'm going to end up with something that looks like this. Now I could have used any of the pairs of electrons that I wanted. I just chose those bottom ones fairly randomly. Now let's do a check again. Oxygen sees 8. Oxygen on the right sees 8. Carbon in the middle sees 8. Everybody's happy. We passed our happiness check, and then we count our electrons, which is 2, 4, 6, 8, 10, 12, 14, 16. That's what we should get. 16 valence electrons is what we started with, and so now everybody's happy. So I'm going to write down what we just did, which is one last happiness check as step 8. And that is how we draw Lewis structures for molecules. Follow those rules in order. Don't go out of order. If you make a mistake at the end, if your happiness check is really, really weird, go backwards in order. Don't try to go back 3 steps and fix that step. You got to undo all the stuff you did to get there, or just start over. They're really hard at first. They take a long time for the first 10 or 20 that you do. After that, you start to get really the tricks and tips about doing this, and you start to learn some of the patterns that you see. But if you do this, if you follow the steps, you will always get the right answer in this class. There's some funny exceptions and stuff that happen to certain molecules. We're not going to cover that in this class. So if you see other videos talking about that, we don't do that. We just do basic octet rule, try to move these guys around to make everybody happy, and it all works out. Thanks so much.